Welcome to this explainer. Today, we're diving into something absolutely mind-blowing in the world of planetary defense. For decades, our go-to plan for stopping a massive asteroid heading toward Earth has been, well, pretty basic. Build something incredibly heavy, launch it into deep space, and just smash it into the rock as hard as we possibly can. But what if we didn't have to rely on brute force? What if we could actually tune in to an asteroid's natural rhythm and just gently nudge it out of the way? Well, that's exactly what we're going to break down for you today. Here's a quick look at our agenda for this explainer. First up, we'll look at the asteroid deflection problem itself. Then we'll introduce the THD resonance hypothesis. After that, we'll walk through the 3 phases of THD. Fourth, we'll look at real-world execution mechanisms. And finally, we'll cover falsification and measurement limits. All right, let's jump right into Section 1, the asteroid deflection problem. Okay, to really grasp this, we need to look at the foundation of this entire briefing. It's all based on the pioneering Triune Harmonic Dynamics, or THD research, authored by Kevin L. Brown, who is a brilliant researcher, inventor, and author. He's making a huge claim here. He's challenging the old-school idea that asteroids are just these giant, solid, dead rocks. Instead, his research points out that they're actually complex structures, and if we treat them like structured bodies, we can use a whole lot less energy to move them just by tuning into their measurable structural resonance. So this specific method is called Harmonic Resonance Deflection, or HRD for short. Now, if you're wondering how this works, just think about pushing a kid on a swing at the park. You don't run up and shove the swing with all your might, right? You just give it a tiny, gentle push at the exact right moment, over and over again. Because you're matching the natural timing or frequency of that swing, you build up a ton of momentum with barely any effort. Well, HRD uses that exact same physical principle. We're just applying it to asteroids so we can safely shift their path without blowing them up into a deadly cloud of space shrapnel. This really is a complete paradigm shift. On the left side here, you've got the standard approach: brute force, kinetic impacts, big explosions. It's basically asking, how hard can we hit this thing? But on the right, you have HRD. This asks a totally different question. Can we vibrate this asteroid into a more responsive state before we try to move it? By using tuned resonance to build up internal stress, HRD could drastically reduce the amount of energy we have to actually launch into space. Which brings us to Section 2, the 3 phases of THD. To see how this actually plays out, we've got to look at the step-by-step framework. And don't worry, there's no sci-fi magic here. It's just solid structural dynamics applied to a space rock. The THD model breaks everything down into 3 strict phases: base, pressure, and integration. So phase 1 is the base phase. During this phase, the asteroid is just doing its normal thing: stable orbit, stable spin. Our only job here is to watch and measure. We need to figure out its mass, its bulk density, how fast it's spinning, and most importantly, its natural resonant frequency. Because let's be real, you can't tune into a rhythm if you haven't figured out what that rhythm is yet. Once we have that, we move right into the pressure phase. This is where things get really interesting. We introduce an external driver, basically a tool to apply force, and we tune it perfectly to that natural frequency we just measured. As we pump that tuned energy into the asteroid, structural pressure literally starts building up inside the rock. We'd actually be able to measure this happening. We'd see the vibrations getting bigger, surface rocks starting to shift around in patterns, and even localized heat building up. The asteroid is soaking up that energy and getting stressed out. And that leads to the final step, the integration phase. Eventually, that internal pressure hits a breaking point. The asteroid physically cannot hold all that built-up strain anymore, so it has to do something to release it. And it does that by changing its physical state. That could mean it speeds up or slows down, its orbit shifts, its spin changes, or it might even shoot material off its surface. The asteroid literally reorganizes itself to relieve the pressure we created. Okay, let's move on to Section 3, real-world execution mechanisms. Now, you might be thinking, how do we actually do this? Because there is one massive constraint we have to deal with here. Space is a vacuum. Sound does not travel through empty space. We can't just fly a massive speaker out there and blast the asteroid with a heavy baseline. We have to physically couple that resonant energy to the asteroid's structure. So how do we pull that off? Well, the hypothesis gives us some really cool practical execution mechanisms. We could use laser ablation, basically zapping the rock with lasers in a rhythmic pattern to create tiny thrusts. We could use microwave heating to pulse heat into the asteroid and expand it rhythmically. We could even land a probe and drill physical actuators right into the surface to shake it. Or we could use tiny, perfectly timed kinetic impacts. All of these methods let us deliver energy at a very specific, tuned frequency. But we can't just apply this force randomly. The research shows we have to target very specific structural spots to get the most bang for our buck. We're looking for the exact place where are pushing perfectly to the whole asteroid's momentum. That might be the center of mass, a major weak point like a fault line, or what scientists call mode antinodes, which are just the spots that naturally move the most when the asteroid vibrates. It is all about maximum efficiency. And finally, Section 4, falsification and measurement limits. Now, any good scientific theory has to be testable, right? You have to know what would prove it wrong. And the author, Kevin L. Brown, lays out some very strict falsification conditions here. For instance, if tuning the energy doesn't work any better than just hitting the rock randomly, the hypothesis fails. If the asteroid's reaction is just total chaos, it fails. And most importantly, if the resonance just blows the asteroid into a bunch of dangerous pieces, what researchers call fragmentation dominating, then yeah, this method is off the table as a safe planetary defense tool. It really comes down to this super simple plain English test. If you take a specific amount of energy and apply it using this tuned, resonant method, it absolutely must create a bigger deflection than if you used that exact same energy to just hit the asteroid normally. It has to win, joule for joule. If the tuned method doesn't significantly outperform the brute force method, then the harmonic resonance deflection hypothesis is totally falsified. So to prove this works safely, the research lays out a really smart step-by-step experiment path. We're not just jumping straight to blowing up an asteroid in space. We start with step 1, testing fake asteroid rocks in a lab. Then step 2, testing them in vacuum chambers to make sure the energy transfers without air. Step 3, testing it in microgravity up in orbit. And then, only if all of that works perfectly, step 4 is launching a small test mission to a harmless asteroid out in deep space. If we can validate this through those rigorous tests, this elegant, energy-saving method could completely change the game for planetary defense. It really makes you look at asteroids differently, not just as dead rocks, but as complex structures we can carefully control. It leaves us with a pretty incredible thought. If a massive asteroid is ever heading straight for Earth, could the secret to saving humanity simply be finding the right frequency? Thanks so much for hanging out with me for this explainer on Triune harmonic dynamics. Stay curious.